In the last lesson, we talked about harmonic waves and also discussed how two harmonic waves interfering at a point can be a constructive interference producing a bigger wave or a destructive interference producing no wave. That concept we will use today to build a new concept of harmonic stationary waves. Now, what are stationary waves? The word stationary suggests that it's not moving. Is that right? Stationary waves. Can a wave be stationary? Well, first of all, let's look at the direction of displacements of particles as the wave advances in a medium. Now remember, the profile of a wave is created by the phase of vibration of each particle, because each particle in the medium is going to be in a different phase of vibration. As the energy of the wave passes through the medium, we get the profile of a wave. Now, if you look at a wave on a crest and a trough, if a particle is on the crest of a wave, tell me, what is the direction of motion of that particle? A particle on the crest of a wave has actually reached the peak and now it is beginning to move down. So this particle is now beginning to move down. How about a particle on a trough? A particle on a trough has reached the lowest possible point in its displacement and is now beginning to move up. That means the direction of motion of a particle on a crest is opposite to the direction of motion of particle on a trough. Therefore, what will happen? What will be the state of vibration of a particle which is subjected to the crest of one wave and the trough of the other wave? We talked about this in the last class. If this particle is on the crest of one wave and the trough of the other wave at the same time, that means wave 1 will want this particle to move down. Wave 2 will want this particle to move up. What will this particle do? Well, it will not move. It will stay at the equilibrium position. There you are. So here we have a particle here which is supposed to be on the crest of the red wave and the trough of the green wave. What will that particle do? Well, it will have no displacement. The displacement produced by the green wave will be cancelled by the displacement produced by the red wave. The particle will stay at rest. Well, so the result of such a superposition is what we call destructive interference. Now, stationary waves are actually formed by the constructive and destructive interferences of two waves advancing in the opposite directions. We will have a look at that as we go on. If the particle is on the crest of both the waves, then the displacements will add up and superposition will be constructive. So when there is constructive interference, the displacements of the particles will be maximum, and when there is destructive interference, the displacements of the particles will be zero. Now, this is an example of constructive interference. The particle is the red wave and the green wave produces displacements in the same direction. Therefore, the total displacement will be the sum of the two. You got a bigger wave. A constructive interference results in a bigger amplitude wave. You can see a bigger wave means a bigger amplitude. a destructive interference will result in no wave at all. So two waves meeting at a point can interfere constructively or destructively, producing a bigger wave or sometimes no wave at all. Now we are going to now use this concept to construct the concept of stationary waves. Now this is a mechanical vibrator. This vibrator can be made to move up and down, producing a vibration on the string that is attached to it. You can see a length of string is stretched between the vibrator and the pulley, and I have used a weight to stretch the string, in other words, to produce the tension. Now listen carefully here. When the vibrator vibrates, a disturbance is created. Now the disturbance advances along the string, and when it reaches the pulley, it gets reflected. That means the energy gets reflected and it comes back here. Now by the time the energy comes back, if the vibrator is ready for a fresh vibration, the two energies will add up. In other words, the energy of the returning wave and the energy that is produced by the new vibration are in phase. You see that? Now that will produce a bigger wave. So what is the criteria for that? The criteria is, by the time this particle completes one vibration and ready for the next vibration, during that time the wave produced by the first vibration must go and come back. Then these two will be in phase. Well, a mechanical driver attached to one end of a stretched string sets that end into up and down vibrations, sending wave pulses down the length of the string. Now these wave pulses get reflected at the pulley. That means you have an advancing wave and a reflected wave. Now what happens as the advancing wave and the reflected wave interfere? Don't they interfere? Well, each segment is now subjected to the advancing wave and the reflected wave. Now how will the vibrations of each particle be affected because of that superposition? Each particle on the string is subjected to displacements due to the advancing and reflected wave. Alright, let's now talk more. Now the green wave is the advancing wave. Here is the advancing wave, and the red wave is the reflected wave. So you must understand that the green wave is moving to the right and the red wave is moving to the left. Now let me see if I can construct that on a very clumsy model here. Now this is the green wave, and I could not find the red one, so I'm using a white one here. Now the advancing wave and the reflected wave. So the green wave is going to go to the right, the white wave is going to go to the left. And you can see at some time, look at this, how they superimpose. You can imagine at a particular time the crest of the green wave and the crest of the white wave are together. That means a particle here will have maximum displacement. The trough of the two waves are together. The particle here will have maximum displacement. Now watch. The direction of motion of the green wave is to the right. Is that right? Now watch me do that. The green goes to the right, the white goes to the left. And as a result, what is happening now? Now the crest of the white wave falls on the trough of the green wave a little later. You see? So as the waves advance, Now they are in phase. So the advancing wave and the reflected wave meeting at a point with the crest of the advancing wave on the crest of the reflected wave, the trough of the advancing wave on the trough of the reflecting wave. What will happen? The instant when the crest and trough of both waves coincide, the string segments have maximum displacements. Everywhere on the string, the particles will have maximum displacements because both these waves are meeting in phase everywhere. So the string segments will have maximum displacements. But this only stays for a fraction of a second. Why? Because the green wave is advancing to the right and my white wave is advancing to the left. Now you can see they are now in phase. Now the green wave advances, the white wave also advances. What is the situation now? Now the trough, the crest of the white wave is on the trough of the green wave. That means what will be the state of vibration of particles then? Now this situation happens only for an instant because the waves are advancing in the opposite directions. Soon the crest of the advancing wave will fall on the trough of the reflected wave. The green wave is the advancing wave, the red wave is the reflected wave. Now look what happens. Now particles, particularly here where the crest of the green wave and the trough of the red wave fall, that particle will have no displacement. That means the particles all over here will have no displacements. Since all the segments now are subjected to opposite displacements, they will remain stationary. That means none of the segments will have any displacements when the situation is like this. But this again will stay only for a fraction of a second. Now this process will repeat. Why does it repeat? Because one wave is advancing to the right, the green wave is advancing to the right, the white wave is advancing to the left. Now watch once again. Now can you see they are in phase? As they move, they become out of phase. There you are, they are out of phase. And now they are in phase, and so on. So alternatively, they come in phase and out of phase continuously. And what is the result? When the string segments, when the advancing wave and the reflected waves are in phase, the string segments have maximum displacement, and this is what you see. Now some points on the string will be permanently at rest. You see, a point here will be at rest all the time. They will not have any displacements at all. And some particles will have maximum displacements, minimum displacements, maximum displacements, minimum displacements. It will appear and disappear. And that is the reason why we call it stationary waves. You see, although stationary waves are caused by an advancing wave and a reflected wave, what you will see on the string are the string particles will have maximum displacements, minimum displacements, maximum displacements, minimum displacements. They appear and disappear. In other words, the wave seems as though it is not advancing. Some points on the string will be permanently at rest. For example, this string has 1, 2, 3 points which are permanently at rest. And such points are called no